With the ongoing buzz around DeepSeek R1 and other reasoning models, folks are looking for a quick but digestible explanation of how these models get trained. All language models are trained using two techniques, supervised and unsupervised learning. In supervised learning, humans provide pairs of input prompts and corresponding expected responses that are then used to train the AI model. An example of such a pair would be, what are LLMs? And then the corresponding proper answer. Another example would be, summarize the attached document, followed by a human-created summary of that document. When the input prompt is ingested by an AI model, it is used as an input into a series of cascaded calculations, with one calculation feeding the next in a layered manner, which eventually results in a single output token. However, these compute layers have no knowledge of anything. The knowledge of a model comes from a large set of numbers that encapsulate what the model is going to learn. These numbers, when combined with the input prompt by the computational layers, produce the outputs of the model. These numbers are called the weights or parameters of the model and can be anywhere between a few thousand to hundreds of billions of unique numbers. Prior to training, these weights are set to random numbers that contain no knowledge, but through the process of training, they are slowly transformed from random gibberish to organized set of numbers that contain knowledge, but that still look like gibberish to us human beings. So, an untrained large language model, or LLM for short, starts with random gibberish weights. To teach it, we present the input prompts to this untrained model, and we get it to produce an output, which will likely be garbage to start with. But the supervised training algorithm is going to compare that garbage output with the expected response and use the difference to create small updates to the random model weights. So now the weights have just become a little bit less random. Now we run hundreds of thousands of pairs of inputs and expected responses through this flow, repeating the process until the difference between the output of the model and the expected response gets really, really small. At that point, we have a trained model. And for the majority of modern AI models, a relatively straightforward algorithm called stochastic gradient descent is the most widely used type of algorithm for updating the random weights based on the error between the model output and the expected response. By the way, that algorithm is based on calculus that some of us had to learn in school, and so maybe it's not as straightforward as it seems. Now, one would think that we're done here, but this is only the pre-training stage for the model. Once a pre-training is done, the LLM is then fine-tuned for a specific purpose. For example, if we want to specialize the model for medical queries, then we can start feeding it medicine-related input-response pairs so that the model may have a better grasp of medicine. We use the same flow and the same algorithms to nudge the general-purpose model to become a fine-tuned LLM for medicine. Or alternatively, we can subject the model to many math questions and their answers to get a fine-tuned LLM for math. This phase of tuning, which is called supervised fine-tuning, or SFT for short, is a very well-known technique in AI and likely used by all the big model creators. Now, unfortunately, even after an LLM is trained and fine-tuned with supervised learning methods, it is not yet ready for deployment. It is still prone to some hallucination and may sometimes generate unsavory responses. Now, to reduce these unwanted effects and to make the model more aligned to the expectations of humans, we use the unimaginatively named unsupervised learning algorithm. Now, here's how it works. We take the previously trained or fine-tuned model and we present it with a sequence of inputs, just like we did before, and we let this model generate a response, which is then fed to the unsupervised learning algorithm along with the input that the model saw, which is a slight variation to what we did in supervised learning. Now we want that unsupervised learning algorithm to further tune the weights of the models so that it hallucinates less or gives more insightful answers or be more polite. But hang on a second. We've not given the learning method any expected responses. So how do we expect it to update the model weights? And that is what is different about unsupervised learning. Instead of an expected exact response, we give it a general score that reflects the quality of the response. For example, we can get some humans to read the responses, grade them as good, bad, or okay, and then give these grades to the unsupervised learning method. This unsupervised learning method that we just described is known as reinforcement learning, or RL for short, and is used to align all LLMs to human expectations. Now, this reinforcement learning algorithm is insanely complex and takes a very long time to improve the model. It requires massive amount of computer resources. Now, why is that? Well, what we are asking the RL to do is akin to a mouse trying to find its way through a maze. It has no way of knowing what path to take. It will likely take many random paths, and it's going to make many mistakes as it slowly learns from its mistakes how to find its way out. The RL model is doing exactly the same thing. It starts off trying random changes to the weights to see if the answers are more palatable to humans. In the process, it goes down many wrong paths, but it tries to follow through on the promising ones. So, at the heart of this algorithm, there is a trial and error method that seeks to capitalize on promising changes. And because RL is adjusting billions of weights, it needs a large amount of time to tune the LLM. Now, in practical deployments of RL, having real humans in the loop would really slow things down. And so humans are usually replaced by a smallish AI model that can assess the responses and assign them a score. Or, if the output of the model that is being trained is an executable code, then we can just compile the code to see if it works and whether it produces the right results or not. This makes training a little bit more feasible, but the random exploration that RL has to still make makes this algorithm insanely slow and very computer intensive. And this has motivated hundreds of scientists to create thousands of variations on the basic algorithm of reinforcement learning. Each one of these variations are trying to make it faster or make it more effective at improving the model. And so, to summarize the training process, we start off with an untrained model that has useless random weights, and we apply supervised learning using a wide set of general language inputs to give us a trained LLM. This is the pre-training phase that results in a model that can hallucinate or produce data that humans find unsavory. Next comes the alignment phase to mitigate some of these issues and align the model with human expectations. It starts off with doing supervised fine-tuning of the model using inputs and response pairs that pertain to specific tasks like reasoning, knowledge, or creative writing. This fine-tuning phase gives us a model that is better suited to the task, but has only learned what information we gave it within the training data in an explicit manner. The real magic happens in the final reinforcement learning phase, where the model learns approaches that have not been explicitly described to it in the training set that we gave it. Next up is our lecture on why DeepSeek is so fast and so cheap and so good. The link is in the description section below. Thank you so much, and best wishes to you.